Hello, everyone. Hello, hello, hello. Good evening, good early afternoon, whatever you want to call it. See, my cat's been working on my setup again. That's so helpful. Little butt monkey. Can't take her nowhere. Urgh. Oh, that's pretty good. Anyone have any questions before we get started? I don't hear anybody talking, and earlier today I had some problem with my speaker that I thought was my speaker talking to you guys. So chat to me if someone's talking and I can't hear them because I can't hear anybody. Can everyone hear me at least? Can someone chat me that?
Yeah, we can hear you.
Oh, cool. Now I hear your voices too. Excellent. Thank you. All right. So last time, let me turn to my lovely face. So last time we were finishing up chapter 4, right? So today we're starting chapter 5. I want you to know I put extra links to YouTube videos from other classes. Basically, I put access to everybody's 241 classes that I'm teaching this semester. It turns out that in one class, they didn't get a instance of an inclined plane Atwood machine, actually in 2 classes. But in one class, they didn't get an instance of me solving a problem for the fuzzy dice. If you remember, I hung some fuzzy dice from a rear view mirror of a car and used that as an accelerometer. So I might be telling you about a problem that you didn't cover, but I just want to make sure you know, you can look at the videos and just fast forward through them if they're problems you've already seen before, or if there's a problem that you have seen before, but I made a mistake on, that'd be a good time for you to watch it over because maybe I corrected it. Remember, we, for instance, made I think it might have been this class where I made a mistake on the Atwood machine in solving for the tension, or this might have been the class where I actually left it up to you to solve for the tension. So there's another one out there where I did it and solved for the tension. So all of those videos are really good. Your display is smaller due to bandwidth. Okay. All of those videos turned out pretty good. There is one where I actually made a mistake and I actually left it. I went ahead and put it on YouTube anyways, because I think it's useful for you guys to see if you can catch the error when I make it, because that's sort of the big deal, is being able to pay attention to what's being said, how I implement the equations, and then look, does he actually say what he's doing? And in this case I did, but I didn't write what I said. So y'all can catch that anyways. But you know, there's also a lot of dead times, like me introducing the class, stuff like that. You can just flow through that till I'll start writing on the pads if you want, and that'll save you some time. But I wanted to let you know I'll be putting more up there as well for both 241 and 242, so you can still access that next semester, no matter who you have for lecture next semester, assuming you take it. So does anyone have any questions before we get started on chapter 5? Okay, looks like
I thought we were finishing up chapter 3 and starting chapter 4. Am I wrong? I'm so sorry.
Yeah, 4 was what we finished last time. It's just yeah, you might be remembering there was a video that said 910, and that was chapter 3 being finished. This past week we finished up chapter 4, which is Newton's laws of motion, but without friction, without
okay.
Sort of thing.
Thank you. Sorry.
No problem. People make that mistake all the time. It's all good. So this one, we start off with chapter 5, and we're basically just going on the assumption that you now know Newton's laws. Now, what that means, and I hope you guys take this to heart, but whenever you take a course where a whole chapter is named after something, then there's a good reason to believe that you better memorize those things as the bare minimum for that particular course. So like we had a chapter on Newton's laws, so not only should you know Newton's laws, you should know exactly which one's the first law, which one's the second law, which one's the third law, and be able to state them accurately. So ideally, accurately would be in your own words, but if you're not quite there yet where you don't understand them well enough to put them in your own words, then by all means memorize them in the quote unquote correct words that your textbook or I give you, and then slowly, hopefully you can make better sense of it. So that's just a rule in general. You know, if you cover something in a course and the whole chapter is called enthalpy, you should probably know what enthalpy means. Gibbs-Duhem equation and stuff like that. All these things are just important topics, so keep that in mind. Also, if you actually cover a course called mechanics, you should be able to define what mechanics is. So all that stuff is sort of the thing that you miss for the tree. So I just wanted to remind you of that, because I've had numerous instructors that really crack you up. You take a whole graduate level course on Maxwell's equations, and like the first test, they say, hey, state Maxwell's equations and give the boundary conditions. And that's like a beautiful question. It's just perfect. I mean, everybody should know that at that point in the course, but a lot of people didn't get it right because they're like, oh, I didn't know I needed to know that. Well, why would you think you don't need to know that? So anyways, I realize I'm having some bandwidth issues. So I suspect you are getting a lot of jiggly video and pixelated video. So the good thing is when the video is done, because my side looks good, the video should look a lot better in recording form than it does right now. So I'm going to start off with just talking about friction, because it turns out that friction is a very, very important thing. And it's part of the reason that I did so much with the normal force in chapter 4. Remember, the normal force we found, at least in the simplest case, was actually equal to the weight of the object. But then I said, well, okay, what about if you have a box being pulled along a surface, pulled at some angle above horizontal? Well, then you saw the normal force would decrease. And in fact, I didn't do this, but if I pulled it downward, in other words, below horizontal, then we'd find that the normal force would actually increase. And then by the time it was all said and done, we also learned that on an incline, the normal force is not equal to the weight. So a lot of the last chapter was about teaching you about the normal force so that you could actually use it, because it turns out the friction force, which we're getting ready to discuss now, is really the equation that we use is basically that it's either proportional to or less than or equal to the normal force times some constant. So I want to start off with you trying a demonstration on your own. Ideally, hopefully you're somewhere where you have a table surface, a desk surface or something like that. And hopefully you have something like perhaps a calculator that's got little rubber nipples for feet, so they're a little bit more sticky than just a piece of plastic on a piece of hard, shiny wood. Or maybe you have an otter box that has a little sort of grippy rubber front edge, and you can just lay it down like this. Because what I want you to try is I want you to take and lay whatever has some innate ability to grip the surface it's laying on. So if you don't have something with rubber like that, try your textbook or something heavy and lay it down on the surface, sort of like, okay, my camera will not show that low. So sort of like this, okay? And what I want you to do is just push, say with your pinky, ever so lightly, and then push a little harder, and then push a little harder, and then push a little harder. But what I want you to realize is that you can push harder and harder and harder, and it won't move. And then all of a sudden it does move. Okay. Not only that, when it does move, you'll notice that's a kind of good sized force compared to all the other ones you did. And then when it starts moving, to keep it moving, it's a much smaller force. That's a key observation to make regarding friction. Okay. And for instance, it's the reason that meteorologists tell you whenever we have a snowstorm, which is like never, but when we do have a snowstorm in this area, the meteorologist will tell you, remember, if you go into a skid, make sure you turn into the skid. And we're going to talk about why that's so. So what it turns out is that the kinetic friction is actually smaller than the static friction. So when the object is not moving with respect to its surface that it's sitting on, the friction force has the ability to be larger. When the object is actually sliding along a surface, that friction force is smaller. And it turns out, believe it or not, that when your tire is rolling by on a car, the bottom portion of that tire has a 0 velocity with respect to the road. And this is something weird that not everybody gets. So I'm going to prove it to you using our relative velocity equation. So let me stop and turn on my document cam, or let me just do some other random thing that has nothing to do with anything because I pushed the wrong button. So this is going to be a car tire. Okay. And this will be the center of the car tire. This will be the top, and this will be the bottom. Okay. What I want you to imagine is it's a car tire or a truck tire or whatever, right? Something like that. Now let's imagine that the car is actually moving at 60 miles per hour to the right. So I'm going to call that the velocity of the car with respect to the earth. And we're only dealing with one dimension, so I can call that a vector just by putting a plus on it, right? Just by recognizing that going to the right is a plus. Now, what I also want you to realize is the velocity of the center, which happens to be exactly the same sign, by the way. The velocity of the center of the wheel with respect to the earth is also equal to plus 60 miles per hour. That's why I didn't even bother changing symbols or anything like that, okay? Now let's imagine the same car reading the same speedometer reading, but this time we got it up on the lift, you know, like they have in garages where they work on them. And when you have that, I think you will agree that the velocity of the center of the tire is, of course, 0 when it's up on that lift. And I suspect you would agree that the velocity of the tire, of the bottom of the tire, so I'll call that V bottom, with respect to the car, because now we're measuring everything with respect to the car, I think you would say that's equal to negative 60 miles per hour. Does that make sense that the bottom of this tire would be moving at 60 miles per hour if the speedometer is reading 60 miles per hour there? And the velocity of the center with respect to the car is, of course, 0. And then the velocity of the top with respect to the car is equal to positive 60 miles per hour. Does everybody agree with that? Any questions on that? Okay. So remember that the velocity of the bottom of the tire with respect to the earth, remember, all I got to do is make sure this is the outermost suffix, or excuse me, subscript, and this is the other outermost subscript. So I just got to write V bottom with a blank here, plus V blank here with an E on the end. Since that outside one and that outside one matches, I know I'm right. I just got to find out some letter to put here. Well, I happen to have the velocity of the bottom with respect to C, so maybe I can put the C here. Well, that works out great because I have a velocity of the C with respect to E. I have the velocity of the bottom with respect to C, and now I can determine the velocity of the bottom of the tire with respect to the earth. And I think you all see that that would be the velocity of the bottom with respect to the car is negative 60 miles per hour, plus the velocity of the car with respect to earth is, or excuse me, yeah, the velocity of the car with respect to earth is 60 positive mile per hour. So you get 0. So that's our proof that the bottom of this tire is actually not moving with respect to the ground. And hopefully in retrospect, that's like a duh moment, because I normally have a word for when a car or tire moves with respect to the road. Anybody have a name for that, or recall what the name, a name might be for that? One's a 2-word name and the other one's a 1-word name, but both of them start with the letter S. At least the first word of the 2-letter name does, or 2-word name does. Anybody?
Skidding?
Skidding, yes. Or spinning out, right? If you spin out, That's the very definition of the tire moving with respect to the road. So yeah, under normal circumstances, the tire is not moving with respect to the road. So that proves that this is static friction. And that static friction is exactly the reason that meteorologists tell us to turn into the skid, because when you start to skid, your car is moving in a way that's inconsistent with the way that the road appears to be moving under it. So if you turn your wheels while you're skidding, say this way, you turn your wheels sort of that way. If you haven't gone too far on the skid, say you're only skidding like this, and you turn your wheels this way, your wheels have the ability now to re-grip in a static friction situation. So when your back end comes around like this, your tires, if you just left them like this, they would continue to skid. But if instead your back wheels came around and you did this, then you would manage to stay straight, which you could also learn from the movie Cars. Okay. You got to turn right to go left, right? And that's really what they're saying. Okay. So all of that, one, shows us the importance of static friction, and two, why we turn into the skid. That's a very helpful physics concept. So now we're going to start to explain what the friction is. So if I make a plot of, let's say, friction, notice I'm using that script F. I told you guys before that this script F is the symbol I use for friction. So that's the friction force, and it's in newtons. And then I'm going to apply a force to a particular object, and that's going to be called F in newtons. Okay, this is the force applied. So I mean applied to the object. And what's going to happen is basically, if you apply zero force, zero friction force will act. That makes sense, because friction is not going to just make this car take off that way, right? But if you apply a little bit larger force, then the friction force will be exactly equal to that. So this first part of the equation is literally F friction equals force applied. So it's like Y equals X. But then all of a sudden it hits some maximum value, and this is F max. Okay. And when it hits that F max, all of a sudden the force falls down, and the force is now F equals F kinetic, which is equal to the kinetic coefficient of friction times the normal force. And this force right here, I'm going to write it in a different color. This force right here, F max, is equal to mu static times F normal. Because what we're saying is the F static is less than or equal to mu static times the normal force. I should have wrote it like that. Okay. So that's really what the equation is. And this is when you were pushing your calculator or whatever you were pushing, at each force that you gave, the friction would give as much, but then all of a sudden you got to some maximum level and the friction couldn't give anymore. So the calculator or whatever began to move, at which case you felt it was a little easier to push it along. And this less than or equal to just says, hey, the friction force, at least in a static scenario, is only going to be as big as it needs to be up until it can't get any bigger, in which case it's going to be exactly equal to that, and that's it. Okay.
Could you zoom in? Yes. It says your bandwidth's low, and it's like a super tiny screen, so it's really.
Yeah, you can see that graph, hopefully. And it actually probably helps if I can focus it at this distance as well. So everybody sees that equation right here is like Y equals X. And then from here on out, it's just F equals, mu K times the normal force. The part at the top, just in case you missed that, was all these velocities. And then, of course, the relative velocity formula, which is right here. And then me plugging it in. A neat thing you can do with that, by the way, I'm going to go ahead and add it, is if I wanted to know the velocity of the top, with respect to the earth, you'd get the velocity of the top with respect to the center, which is positive 60, plus the velocity of the center with respect to earth, which is 60 miles per hour. So that's 120 miles per hour. So that means basically, hey, if a rock is thrown off the top of a tire and a car is going 60 miles per hour, if you didn't have a wheel well for that tire to be inside of, that could really do some damage. Can you imagine hitting someone with a rock that you threw at 120 miles per hour? That'd be serious. And in fact, that's one of the reasons that cars aren't made like this, except for very special circumstances, like, you know, tractor pulls or something like that, because those tires sticking out that far on the sides would obviously cause a problem. Now, if you're in the car and you got your arm hanging out the window, then yeah, this thing's going to be coming at 120 with respect to the road, but with you, it's only moving at 60. But I promise you, getting hit in the arm with a rock at 60 miles per hour is not too fun either. So anyway, so that's the way friction is going to act. So I'm going to give you a couple problems real quick, sort of what I've called before kindergartner level problems of applying Newton's second law of motion. Okay, so let's look at example 1. So example 1, I'm going to imagine a 100.0 kilogram force, or excuse me, kilogram box sitting on a frictionful floor. Okay, I'm going to say that the coefficient of kinetic friction is 0.20. Notice it has no units. It has to, because basically you got to multiply a normal force in newtons times something to get the friction in newtons. So it's got to have no units. But I also want to say that the static coefficient of friction is 0.50. Okay. And I'm going to apply force at 36.9 degrees above the horizontal. So let's say this is a 100.0 Newton force, and this angle is 36.9 degrees, which if you hear 36.9 degrees or 37 degrees, you should automatically be thinking the 3-4-5 triangle. Okay, same thing if you hear a 53-degree angle, you should be immediately thinking the 3-4-5 triangle. So just for a refresher, that's a 4, that's a 3, that's a 5. The 36.9 would be up here. That's the key point. The 36.9 has to be opposite the smaller side. Now, in this case, we had 100 newtons here, so that means you got to multiply 5 by 20 to get that. That also means you got to multiply 4 by 20 to get that, and 3 by 20 to get that. So this side's 60, that side's 80, that side's 100. So that'll help us a little bit later. Now, what I want to do is find out, does it accelerate? If so, what is A? Okay, so I'll start off with my free body diagram. And I'm going to say the mass is 100.0 kilograms. That's going to be M. Okay, I'm going to draw my coordinate system so that up is the positive Y direction, and to the right is the positive X direction. And now I'm going to start adding forces. I know that the weight is going to be acting downward, so I'm going to use red as in the stoplight to record the weight, which is M times G, and of course G is 9.80, so M times G should be 980.0 newtons. Notice that's an extra sig fig there, just because I only know 9.8 to 3 sig figs. There's also going to be a normal force acting upward, We don't know what that is, but we're going to need to find it. Okay. And there's going to be a friction force acting back, and I can't say anything more about it than that. I can't say it's a static friction. I can't say it's kinetic friction, and I can't give its value, because if it happens to be static, it's only going to give as much as it has to. Okay. Now I can also write this 100 Newton force like this. And with that in mind, I know that the angle adjacent to the 36.9 is 80. So this force will be 80.00 newtons. And that's one extra sig fig, because 36.9 only has 3. And this is 60.00 newtons, again with one extra sig fig. Okay. Now you might think I only need the Newton second law in the x direction, but you'd be wrong. You actually have to do the y direction so you can find the normal force. So we'll say the summation of forces in the y direction equals mass times acceleration in the y direction, which I think by now you guys get it, that the a sub y is 0, because we're not considering a box going boom, 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 bouncing up and down. So the y component of the acceleration is going to be 0. The x component is going to be the only possible acceleration, so we'll call that one just plain x, and we still don't even know if that's 0 or not. So right here I can write the vertical forces are F normal, excuse me, plus 60.00 newtons, and then minus 980.0 newtons, and that's equal to 0. So we see that the normal force is actually equal to 920.0 newtons. Everybody see how I got that? So again, in case you're not reading due to pixelation and whatnot, that's F normal plus 60.00 newtons. I've got the last 0 underlined, minus 980.0 newtons. I got the last 0 underlined, equals 0. That led to F normal equals 920.0 with the 0 underlined newtons. Okay, so now I know the normal force. Now that means F max is equal to mu static times the normal force. Well, since mu static is 0.5, I'm going to say 0.50 times 920.0 newtons. That's going to give me 450, gives me 900 plus 10, so that's 460 newtons. That's the F max. So now I can do the summation of forces in the x direction equals mass times acceleration. Notice I left off the x because that's the only acceleration we're talking about. And now what we'll see is, remember this equation basically says if you're below F max, then the friction force will be exactly equal to the applied force. So what we have here is we have 80.0 newtons, 80.00 newtons with the last 0 underlined, minus, in this case, the friction force is going to be, since it's less than 460, it's got to be 80.00 newtons. So that's clearly equal to 0. So A is equal to 0. No acceleration. So I just wanted to argue that out. Basically what we're looking at is 80.00 newtons is the force applied. So this is going to be 80.00 newtons right there. Now, if that force had been greater than F max, then obviously we would have used that much force to get it going. But once it started going, it would just be this quantity, which would be 0.2 times the 920, which obviously you can tell would be more like 92 times 2 would be 184. So that's example 1. Anyone have any questions on that?
Do you mind showing it closer to the camera?
Yes, no problem at all. Okay. Is that close enough?
Yes, that works. Thank you.
No problem. Just make sure everybody sees everything. And this is where we ended up applying the 80 newtons to 80 newtons. Sorry about the bandwidth issue. I know exactly what's causing it. Or that means I've learned something about what I'm not going to do anymore. All right, so let's do example 2. Now this time, example 2 is going to be essentially the same. Actually, no, this time I'm going to apply a force of 1,000 newtons. Would that give me anything good? That would make 800. No, that's still not good enough. Yeah, that's good enough. Yeah, that's good enough. In the previous class, I just reduced this down to 10 kilograms and left that force the same. This class, I'm going to make this one 1,000 newtons and leave the mass the same. So now we have the same block with 100.0 kilograms. We have a force that is 1,000.0 newtons. Ooh. Okay, big Newton force. Of course, it's still only like 250 pounds, so it's not that big. But the angle is going to be at 36.9 degrees again. Okay. And it's sitting on a friction full surface. With mu static equal to 0.50 and mu kinetic equal to 0.20. Okay. And I want to say, is A not equal to 0? And if so, what is A? Whoa. Okay. Now, again, I'm going to have to find the normal force, but I'm not asking for that. That's sort of typical of physics problems. They're going to make you solve for things just because they want to see whether you actually know you have to solve for them, even though they didn't ask for them. Okay, so that's a big trend that goes on in physics, and it's always going to be that way. So be prepared. So really, I'm just asking, what will the acceleration be? I'm going to draw my free body diagram again. I'm going to use the right as the positive x-axis. I'm going to use up as the positive y-axis. I'm going to remember that my normal force points upward, and that's positive, so I'm going to use purple. I'm going to remember that my force F is 1,000 newtons at 36.9 degrees. And of course, using our 3, 4, 5 triangle again, this is 36.9 degrees again. So I have to multiply 5 by 200 to get 1,000. So this one has to be multiplied by 200, and this one has to be multiplied by 200. And now I can break down my components. I'm going to say this one's going to be a 800 Newton force, and this one's going to be a 600 Newton force. Again, I'm carrying one extra digit because now the 36.9 is only 3 sig figs. I have another force acting in the negative y direction. That's the weight, which again is 980.0 newtons. And I have another force acting in the negative x direction, and that's just going to be the friction force, which again, I will not label as anything until I make certain I know what's going on. So what I'll do is take the summation of forces in the y direction equals mass times acceleration in the y direction. Again, taking a sub y equal to 0. So I'm going to get that F normal minus 980 and then plus 600 is equal to 0. So I can see the normal force is actually going to be 980 will come over here and be positive, and 600 will be over here and be negative. So this will be 380.0 underscore newtons. That means F max is going to be half that, which is, well, 360 would be 180. And then I got to half the remaining 20. So that would be 190. Now the summation of forces in the x direction equals mass times acceleration in the x direction. That's going to give me, and I'll write it right here, that's going to give me a force of 800 newtons minus, now in this case, the F max is 190. This exceeds the 190 by a lot. So what we've gotten into now is we've gone beyond this F max point and we've fallen here. Yes, it would take the whole 380, or excuse me, the whole 190 newtons to get it started. But now that we have a force bigger than that, we know it's going to start and it's going to be behaving as if the friction force of mu kinetic times the normal force is the friction force. So 800.0 newtons greater than F max implies that the static friction will be equal to 0.20 times 380 newtons. Okay. So 0.20 times 380, well, it's 2 divided by 10. So I could call that 38 and then multiply that by 2. And that, of course, would be 76. So it's going to be 800 newtons minus 76.0 newtons. That's really only 2 sig figs, so I have to put that as a 0 there. And that's going to be equal to 100.0 kilograms times the only acceleration that exists, which is a in the x direction. So the a is going to equal 800 minus 76 divided by 100. When you get 800 minus 76, that's clearly 724. So divided by 100, that'll be 7.24 meters per second every second is the acceleration. And just for the record, I'm saying this is 724.0 underscore newtons. That makes sense to everyone? Easy peasy, right?
For the most part.
Do we need to bring it up close to you again? So that's really what Newton's laws are about, is basically breaking down components of forces. If you draw them in the free body diagram, breaking down the components of the forces in the X and Y directions, and then setting them or putting in the appropriate place in Newton's second law. And sometimes you'll have some weird little thing like this, where, you know, you have a force of friction that's less than or equal to something. Now, in your statics and dynamics classes, they will actually give you a sort of algorithmic way where you can just apply it every time when you have something like a static friction and kinetic friction and stuff like that. We don't do that. We're wanting you more to sort of fly by the seat of your pants and figure it out at each instant. I think that's good. I like it. But at the same time, I do not think it's bad that they get engineers to do it the other way, because the engineer is, when you go to take your fundamentals of engineering and your other engineering tests, you're allowed to bring in basically any number of books that you want to. So they try to write these books where they have very distinct rules about how you do things. So you can immediately say, oh, I can pull this open. I just remember this algorithm and I'll apply that. And that kind of thinking will keep a person that's, say, designing a bridge or a building, which could obviously cause death and mayhem if they failed. That keeps them to thinking algorithmically and not going too far astray and taking chances so that they don't risk lives. So I think that's a good thing for the engineer as well. But I think as a physicist, we're wanting you to be a little more creative every time. So not to say that an engineer can't be creative. They certainly can. They're going to be. It's just saying that the physicist wants you to be creative right now. The engineer wants you to be creative early, but not when you get out there in the field, unless you have evidence and experimental data to back you up. I've seen people, for instance, I worked in structural engineering for a while, and things were done that I didn't really care for, and I couldn't find any evidence that anybody had done the experiments to show this. But basically, like, I would see an engineer advise me to take a point load and to, sort of divide it up over a whole beam and apply it to the beam as if it's a load per unit foot. I'm okay with doing it the other way, where you take a certain load per unit foot and find the centrum of that force and then apply that at that point. And that gives you a little margin of safety because it's a lot harder, at least in shear. It's a lot harder to meet the demands in shear for that situation, but not the other way around. And I never found anybody justifying it. So I was always taken aback when an engineer would tell me that. I was never a licensed engineer. I never took any. In fact, I was in the process of applying to take the fundamentals of engineering exam. And I actually qualified for it, but it was going to take a little bit of an act of Congress because they had just made it where you had to have a engineering or pre-engineering degree, and they had just stopped taking physicists for it for some reason. But you could appeal, so I was in that process. But anyways, that's something you got to watch out for. Is if you go out into engineering and you're doing something, you can do a little fast and loose to get an order of magnitude idea what you're going to do, but never apply that in the actual field for something that you're going to turn in as a spec for a beam or something like that. You need to find some evidence backing that up. So you look in the journal for structural engineering or something like that to see if anybody's done anything like that. But point loads are a very dangerous thing. And if you take and spread them over a distance, you're not necessarily doing something accurate. So be careful with that. Other things they use were like flitch plates, and they just assume that the flitch plate is the strength of the plate plus the strength of the 2x4, 2x6, 2x8, 2x10, 2x12, whatever you used on one side, plus that one. And in actuality, that was a conservative estimate, because it turns out as a beam, when you bolt them together, they act a little bit even better. So in that case, you were being conservative and you were erring on the side of more safety. So that was fine, but you just got to watch out for stuff like that. So anyways, now that's how we deal with friction. It's not that big a deal. You can apply it over and over again. And in fact, you can find cases where friction is really what is the thing that saves you. For instance, when you bank a curve to design a road, you bank that curve, for instance, to make sure that the normal force alone is sufficient to supply the centripetal acceleration to make the curve. In other words, in an icy situation, if you're going the speed limit, you're still not going to slide off the curve. But of course, if you're speeding, then you are going to slide off of it. And if you're going too slow, then you're going to slide down and hit the guardrail on the inside of the escape ramp. So just keep an eye on that kind of stuff, but you'll see how to do that. What I want to do now is introduce you in a sort of unique way that I do with my students. I'm going to introduce you to a way of determining the centripetal, that center-seeking acceleration. And it's good because it teaches you a way to derive it. And this is a very important concept. I'll even tell you a horrible story about some people dying because they didn't know this particular piece of information. And I'm not laughing about that by any stretch of imagination, but I just wanted to advise you that is, what happens when you go off and do things that you're not quote unquote educated enough to, or knowledgeable enough to understand how to do. So again, I say knowledgeable enough or educated, because you can actually get a lot of experience by doing things other than just going to class. So let's start off with a big circle. And I really didn't mean this big of a circle, but here we are. Okay. What I'm going to do is imagine an object going in a circle and try to assume it's going at a constant velocity around that circle. And in fact, I'm going to force that to be the case, and you won't even necessarily know it. But in doing so, I'm going to find out what acceleration is necessary to make that happen. So there goes my ultimately cool constellation mug. There's Orion right there. There's Taurus, the bull right there. But that's my cup holder that I use. It's my cup that I use as a pencil holder. So what I'm going to do is I'm going to imagine this to be exactly the center of the circle. I have no idea that it is or isn't. I'm going to say that's my x-axis. I'm going to say this is my y-axis. I'm going to say this distance right here to here is r. And in fact, I'm going to define a vector, r of t, as that vector right there. So the length of this vector, by the way, is just plain r, but I'm saying the vector r of t is that vector. I think you can see that obviously this would be at an angle theta. And in fact, this point right here would have the coordinates x comma y, where x is equal to r cosine theta and y is equal to r sine theta. Okay. Now here's the part that makes it a function of time and the part that makes it sure that it's going to complete a circle at a constant velocity. I'm going to write this vector as r times the cosine, but not of theta, not of theta, but of 2 pi over t, which I'm going to call the period. You'll see later by doing the actual graphing of the point. 2 pi over big T times little t I hat plus r sine, again, 2 pi over big T times little t, and this will be in the j hat direction. So I think you can see from that clearly at t equals 0, you're going to get, this one just being r. At t equals, let's say, if I made this 2 pi over t times t equal to pi over 2, then clearly it would be right here. And of course, that would be 1 and this would be 0. So that's what you're getting. So what you can now do is you can say, I want to make a graph of, or a table, if you will, of x comma y, in other words, the coordinates. And I'm going to take it to be at times, let's say, 0. Let's say t over, let's say t over 4. Now let's go ahead and say t over 8. So t over 8, and then 2t over 4, which would be, of course, t over 4, or 2t over 8, which would be t over 4, and then 3t over 8, and then 4t over 8, which would be t over 2, and then 5t over 8, and then 6t over 8, which would be 3t over 4, and then 7t over 8, and then just plain t. And I think you can see that this one's going to be r 0. This one's going to be 0 r. This one's going to be negative r 0. This one's going to be 0 negative r. And this one's going to be 0 0 again. Zero, zero. You can work it out more definitely, though. If I put t over 8 for the time, you can see that's going to be t over t. That's going to cancel out and I get 2 pi over 8. 2 pi over 8 is really pi over 4. And then, of course, pi over 4 we know is 90 degrees. And the cosine of, pi over 4. Is that right? Pi over, yeah, pi over 4 would be 45 degrees. Sorry about that. So this one will be square root of 2 over 2 r and square root 2 over 2 r. So that's that point right there. at 45 degrees basically, and so on and so forth. So what you find out is that each of those times are all these positions right here. There'll be a halfway one right about, let's say here. There'll be another one here. There'll be another one here. There'll be another one here. And another one here. And in fact, when you get to T, you're right back where you started from. Okay. So I would like you to go ahead and, you know, after class or whatever, try to fill in the rest of these time periods and see that you get exactly what you'd expect you to get. So this one's going to be negative root 2 over 2 times R, and then positive root 2 times root 2 over 2 times R. This one's going to be exactly what I got there, and so on and so forth. Okay. Now that we have that, I'm going to make use of something that we know of. We know that the velocity as a function of time is the derivative of the position as a function of time. So I want you guys to go ahead and take a derivative of this. Remember, the R is a constant, the T, the big T and the 2 power constants, and we're taking the derivative with respect to little t. So all you really have to do is take the derivative of cosine of something, and then take the derivative of that something with respect to t, i.e. you got to use the chain rule. And then the I hat, those are actually unit vectors, and they're special unit vectors in that they don't depend on any other variables, unlike those other ones we might use in the future, like theta hat and phi hat and rho hat and stuff like that. Those are actually going to be things you got to take the derivative of. The I hat, j hat, and k hat, you never have to integrate them, you never have to differentiate them. They're always going to come right out in front. So can anybody give me the x component of the velocity? So just take the derivative of this part right here. I'm assuming the speaker's still working, but I don't hear anybody. Remember, the derivative of sine is cosine, but the derivative of cosine is negative sine. So maybe that'll help you.
Can you pull it, your camera or the document close to the screen?
Yes. And here, to make things a little better, go ahead and define omega to be 2 pi over t, and you can just write that as omega instead of 2 pi over t if you want. I'll show you that in a second. Everybody see that? So I'm going to say that omega is defined to be 2 pi over the period. So then I just get R cosine omega t for this one, and R sine omega t for this one. So that's a nice simplification, because omega is going to be a constant as well. Of course, I could have wrote that omega to look a little better, but anyways. So does anybody have a derivative of the first x component here? Okay, that's what you should get, because the derivative of cosine is negative sine, but then the derivative of omega t with respect to t is just omega, so I got negative r omega. Over here, I'm going to get positive r omega cosine omega t j hat. Now here's the cool part. If I want to take the magnitude of v of t, that's going to be equal to the square root of r omega sine omega t negative, all that squared, plus r omega cosine omega t, all that squared. And I think you can see that r squared omega squared can be factored out, and you get the square root of r squared omega squared times the square root of sine squared omega t plus cosine squared omega t. And hopefully everybody knows that what's this is. Can anybody tell me what this right here is?
It's a tangent.
Close. There is a related tangent thing here, but sine squared plus cosine squared is equal to 1. So we get the square root of 1 for that one, and this one just becomes r omega. So what I've done is I suggested to you that this equation for position as a function of time gave me a constant velocity. And what I just showed you is that it does indeed give me a constant velocity. And that constant velocity is basically v, which is 2 pi r over t, because omega is 2 pi over t. So what we get is v equals 2 pi r over t. Again, hold that up so you guys can see that. So since the r is a constant and the time required to complete one circle is a constant, you can see that the velocity is in fact a constant. And not only that, you can see that this one has a negative x component and a positive y component. In fact, this vector is 90 degrees ahead of the position vector. So when I actually draw it on the paper, v is 90 degrees ahead, or you can think of it as, well, yeah, 90 degrees ahead is probably the best way to think about it. But it really points in the direction that the thing's going at any point in time. So when you get, for instance, if you want to evaluate it at t equals t over 4, you'll find that v is horizontal with a negative x component. And if you do it here, you're going to find that v is at 45 degrees with a negative x component. So that's something kind of neat as well. Now we know the velocity. The next part is I want to find out what the acceleration is. So we have a of t is equal to dv over dt. And we know that v of t is just this. So you folks want to try to take a derivative of that for me, and I'll write it up too and see if we get the same quantity. So notice it's negative, v of t is negative r times omega times the sine of omega t, all of that being multiplied by I hat. And then the x or the y component is r times omega times the cosine of omega t, and all that's being multiplied by the j hat. Remember, you don't have to take derivatives of the I hat or the j hat. And remember that r and omega are just constants. So you'll go ahead and do it. I'm going to do it. We'll see if we get the same answers. Okay, hopefully everybody got the same thing I did. There's your x component. There's your y component. Let me focus it a little bit better at this distance. So a is dv dt. The x component is negative r omega squared cosine omega t I hat. And then minus r omega squared sine omega t j hat. Now let's see if you guys can do what we did before and calculate the magnitude of this. So a is equal to the magnitude of a of t. That's going to be equal to the square root of negative r omega squared cosine. All that's going to be squared plus negative r omega squared sine. All that's going to be squared, and you got to take the square root of all that. I think you can see that the common r squared omega to the fourth, when you take the square root of that, that's just going to become r omega squared. Now we have left cosine squared plus sine squared of that same omega t, which again, sine squared plus cosine squared equals 1. So we just get r omega squared. Again, r and omega are constants, so you can see already the acceleration is in fact a constant. Not only that, if I look at the a vector, let's look at the a vector with a little bit different way of thinking about it. Let's say a of t, and I'm going to say it's equal to, I'm just going to pull out a common factor here of negative omega squared times, now I'm going to write r cosine omega t I hat plus r sine omega t j hat. Does everybody see that that is basically just anti-parallel to r? So what that means is this vector a points in, because it was negative I omega squared times the original r vector. Since it's negative, that means it's going to point in the opposite direction. Let me focus on this length too. It's going to point in the negative direction. And of course, omega squared is got to be a positive. So yeah, there's no chance but for it to point inward. And that's called the centripetal acceleration. Now I will focus again. Let's work out in detail another way of calculating that magnitude. So the magnitude of the acceleration a, which is actually what we call a centripetal, is going to be equal to r omega squared. But we already learned that omega is 2 pi over the period. So I'm going to write r times 2 pi over the period squared. Now this doesn't look that helpful to me, but if I multiply by r over r, then I'm just multiplying by 1, so that works. So now I can pull this r and this r inside, and I'll get 2 pi r over t squared times 1 over r. Does everybody see what I just did there? So I'd found the magnitude of the a, which I called the centripetal acceleration. I found that was r omega squared. And earlier we had defined omega as 2 pi over big T, the period. So it's squared there. I then, on a whim, because I knew where I was going, I multiplied by r over r, because you can do that. That's just 1. And now I took this r and this r, since that makes r squared, and pulled it inside of here. So now I have 2 pi r over t, and that whole quantity is squared. Does anybody recall what 2 pi r over t was? Anyone now?
The velocity.
Yes. So in fact, what we found is the centripetal acceleration is v squared over r. Again, focusing that. So we have a new expression. A sub c is equal to v squared over r, and that is the formula. Okay. Now that's kind of a big deal, and we only got 10 minutes left. I would normally like to spend more time on this, but I know our bandwidth is screwing up, so I feel like I'm wasting your time because you really got to go back and look at this. to make sense of it. So let me switch back to my cam for a second. So you've probably seen people doing this on YouTube. So you like go to, by the way, it's illegal, so don't do it. But you go to Arches National Park in Moab, West Utah, and you and a bunch of your friends take and say tie a rope around one of the arches, and then you take the rope and you tie it around some hook, and all you are tied to it, and you jump off and you swing back and forth. Whee, yay, that's fun. Well, in the, I want to say it was the late 80s, but it might have been the early to mid 90s, a guy had started doing this thing, and in fact he was doing it around various mountains and stuff like that, and he had a wild idea. He lived in California. He was going to do it in San Francisco off the Golden Gate Bridge. Well, one thing you should know about the Golden Gate Bridge is it's one of those really, really high bridges that's so high that people use it to commit suicide. So like literally, if you jump off the bridge, there's a high probability that you're going to die just from impacting the water. Even though quote unquote water is supposed to be soft, no, you die from it. Okay, so it's not a good thing. His idea was, hey, I'm having super fun doing these swing things, so I'm going to hook up a system with 5 of us, and we're going to all hang from this cable. We're going to pull it taut, and we're going to swing from the Golden Gate Bridge. It's going to be freaking awesome, right? So he gets the idea. He goes to do it. So he weighs all his friends, all the 5 or 6 people that are supposed to be on there. And let's say, just for argument's sake, he comes up with a weight of 2,000 pounds. Okay. He goes to your local hardware store, Taylor Do It Center, Home Depot, Lowe's, whatever. In fact, I think Home Depot just started existing when this occurred. But anyways, he went and got this cable, and he looked at it, and the cable said something like, again, I'm using just a idea of the amount. Let's say the cable was like 2,800 pounds. In other words, it can sustain 2,800 pounds. He's like, oh, great. This gives me a little safety factor. We weigh 2,000. This cable can hold 2,800. I'm good to go, right? Well, the problem is he didn't quite understand physics. So what happens is, in order for you to swing, or let's say in order for you to hang from the cable, so let's just say we just instantaneously transported ourselves to be hanging from the Golden Gate Bridge at the bottom of the cable, all 2,000 pounds of us. And in fact, since that cable holds 2,800 pounds, 2,000 pounds would be just fine for that. But what we just showed is that in order for you to maintain a circular orbit, in other words, in order for you to travel in a circle, you have to have a certain amount of acceleration that keeps you from going straight instead of curving and staying the same distance away from your pivot point. So, ideally you don't want the cable to stretch, so you want to keep the same distance r away. And in order to do that, you don't need just the weight. In fact, you need the weight plus something related to mv squared over r. It actually is a function of sine. So in fact, this early part, you have more than enough strength. But once you start to get further and further down, you start to run out of strength, because the mv squared over r gets large enough, because the velocity is getting larger the more and more you fall. It gets large enough to completely overwhelm the fact that the 2,000 is reduced by a sine theta. That doesn't matter at all, because you're going to exceed the 2,800 just from the mv squared over r. And that's ultimately what happened. The cable came down. Eyewitnesses said it probably broke around this degree. The cable broke. People hit boats. One person was permanently a quadriplegic. I think one person died. The guy went to jail for this. It's basically involuntary manslaughter or something along those lines. But it was all because of lack of understanding of physics that this happened. And again, I'm not trying to make light of that. I'm just trying to say this is one of those instances where you need to know stuff. And because you haven't been, say, educated in physics, you probably have a great deal of confidence that if you make a cable that can hold, or you take a cable that can hold 2,800 pounds, you're pretty confident that it can clearly hold 2,000, no problem. But that's the problem. When you're ignorant, you don't know what you know. You don't know what you don't know. So that's what happened here. And the poor, like I said, a lot of people were hurt that day. And he was hurt, but he was actually one of the least hurt, but still one person was a quadriplegic. I think one person actually ended up dying. If not immediately, it was in months of the original injury. So that's a big deal. So let me now take this last couple minutes and give you an idea of what we're talking about on this. So with this particular problem, for instance, you can imagine what's going to happen. This is a slightly more advanced problem than the ones we've been solving. So I'm going to go ahead and show you a little bit of it. And I know we get out at 7, so you guys can certainly split when the 7 o'clock rolls around. I'm going to stop right at the 7 o'clock mark probably, but if I go a little bit over, you're welcome to stay or leave. I understand, and you'll catch it on the video. So what's going to happen here is we're going to have an object on a string, and let's say this is the angle theta right here, okay? And all of a sudden I'm drawing it really small when we know damn well I need to draw it big because the video quality is bad. So let's do it like this. So that's my mass M. And let's say this is my angle theta, okay? And this is supposed to be perfectly horizontal, so we can maybe call this the x-axis if you wanted. Now the forces acting on this are the weight, which I'm actually going to do something weird here. I'm going to tilt my coordinate system. So I'm going to draw my weight straight down as W is equal to mg. Okay. Now the other force acting on it is in fact the tension in the rope. Or in the case of the Golden Gate Bridge, it'd be the tension in the cable. But that's the tension. Okay. And as this thing falls downward, we're going to have to accelerate in that way in order to maintain a circle. And in fact, what I'm going to do is I'm going to scratch that x-axis and say I never drew that because I didn't. Y'all can't prove anything. Actually, you can, but we're going to pretend like you can't. So now what I'm going to do is I'm going to draw the positive x-axis this way. I'm going to draw the positive y-axis this way. Okay, and I'm just going to take a snapshot of that in time. So my free body diagram basically looks like this. And what I have is this is an angle theta. This is W equals mg. So in fact, if I wanted to complete the parallelogram, I could see that this would be pointing in the positive x-axis direction. This is the positive y, of course. So this angle down here would be theta. The reason why I know that is because this is 90 degrees. So this being 90 means this little one's got to be theta minus or 90 minus theta. So this one's got to be theta. So I can see that this one's going to be mg cosine theta is that force. This force, on the other hand, is going to be pointing in the negative direction. And that's going to be mg sine theta. Okay. And then finally, we have the tension pointing up this way. So the summation of forces in the x direction is equal to mass times acceleration in the x direction, gives us basically that mg cosine theta, that's in the positive direction, is equal to their mass times their acceleration in the, I'll say just in the tangential direction. So this isn't the centripetal acceleration. That's the main thing I want you to understand. Now the other part is the summation forces in the y direction equals mass times acceleration in the y direction. Now that's the one where you have to have it going with an acceleration this way of mv squared over r. So in this case, I've got t minus mg sine theta. This is what I was warning you about earlier. The fact that you have mg sine theta makes you realize, oh, well, wait a second, I had less than mg. So that 2,000 pounds that we weighed is actually going to be smaller by an amount sine theta, until theta, of course, equals 90 degrees, and then all heck breaks loose. But for right now, we're going to say that's equal to mv squared over r, where the r is the actual length of the cable. Okay. So from that alone, you can see that the tension is going to have to actually be mg sine theta plus mv squared over r for any particular velocity. So yeah, this is going to be down, but once you get to 45 degrees, you're already at square root of 2/2, or basically 0.707 your mass. So instead of 2,000 pounds, it's going to be what, 1,414. So 1,414 pounds at 45 degrees. And then this is going to be basically, let's say the 2,000 divided by 300 is going to give you the actual slugs, and then times v squared over r. This is greatly going to exceed the 2,800, if you will, pounds that the cable came up with. So that's just a back of the envelope showing you how this is related. We'll actually solve more problems that actually are a little bit more solvable than this one. I just wanted to let you see it's this part right here, that mv squared over r makes an addition to the weight that actually causes the cable to fail. So be careful out there. You guys are free to go. If you have any questions, feel free to stick around. I'm going to pull that a little closer to you guys so you can make sense of it, and I will focus in on it again. So there's my big picture. There's my F equals MA. There you go. So anybody have any questions for me?
I had a question.
Yes.
The MyLab homework had chapter 6 homework due. I was confused about that.
As I've said this a couple of times in class, that's why I didn't answer the emails I got. If we haven't covered the chapter, then there's no way the chapter homework's due. So just keep that in mind. We're on chapter 5 now. There's no way chapter 6 can be due. Once we start chapter 6, now then the date should be accurate within that day. So like right now, I'm getting ready to go into MyLab and mastering and make sure chapter 5 homework due date is proper. If it's not, I'm going to change it tonight. But it should be, I think it's already set, to be honest with you. So chapter 5 is supposed to be due Sunday night, a week from yesterday.
Thank you. I thought so. I just wanted to make sure.
Yeah, that's no problem. I get it. You're worried about your grades. And like I said, I'm not trying to be a smart aleck. I just want to warn you. I remember I set these things up and it does all this, and I just don't have much time to correct it in time for you guys. So if we haven't covered the chapter, then know that due date can't be right.
I understand. Thank you.
No problem. See you, Jarrett. And actually, it wasn't Jarrett that emailed me, by the way. Somebody else. Actually, it was several somebody else's. Anybody else have any questions?
Could you go to the previous page? Where we started doing the V of t.
Yeah, the derivatives. Can you see that? Or is the bandwidth still bad?
Yes. Yeah, that's good.
And then the acceleration one, I'll move up slowly so y'all can see that too. So believe it or not, you actually have all the tools you need right now to complete all the problems from chapter 5. But I'm going to spend the next time doing nothing but examples. So anybody else have any questions?
I have a question from the practice test for chapter 3 and 4. I just have no idea what I did wrong on this question. Can't figure it out. And I wasn't sure if you'd have time to go through it.
Let me make it so you can share your screen. So that might be more helpful to you.
Okay, I would think so.
Okay, so go for it, Abby.
Is that displaying?
Yes, it looks good. So the velocity
Okay.
as a function of time initially is 3 meters per second in the x direction and 1 meter per second in the j direction, or the y direction, right? At time t equals 0 seconds. The acceleration is, okay, they give you the acceleration as a function of time, all right? If the object is located that, okay, so yeah. What this is more or less the same thing I did when I did my derivation of the kinematic equations. You're doing exactly that process, only instead of starting with a equals a constant, you're going to start with a equals that stuff. So let me show you what I mean by that. You're going to start with a of t is equal to, and I'm going to get rid of all the units right now. I'm just going to write 2t I hat plus 1t squared j hat. And I'm going to say v0 of t. Actually, that shouldn't be even of t. That should be v of t equals 0. That's going to be 3 I hat plus 1.00 j hat. And that is at t equals 0. So what you know is a is equal to dv dt. And that's dv as a function of time. So what you're going to do is you're going to say the integral of a of t dt is equal to the integral of dv of t dt times dt. Okay, and what they gave you seems to not be that helpful. So the way I'm going to make that helpful is actually in this case, I think I can do it from, yeah, I'll do from t equals 0. T equals 0 to sometime t equals 0 to sometimes t. So when I integrate a of t, you can see what happens. 2t is going to become 1/2 of 2t squared. So that's just going to be t squared I hat. And then t squared, when I integrate that, it's going to become 1/3 t cubed. And now I have to integrate that or evaluate that at t equals 0 and then just plain time t. Okay. So you might want to relinquish, actually, let me go ahead and write one more thing. The R0 of t is equal to 1 meter I hat minus 1, okay, 1 point, let's say 1 I hat minus 1 j hat. And that's actually for t equals 1 second. No? Yeah, it's t equals 0 seconds. So that works. Okay. So I've got that. And what they want to know is what is position? They want to know R of t equal 1.00 seconds. Okay, now if you give me back control, y'all can probably see a better view of my screen.
Yep, give me 1 second.
Yeah, I don't know how to tell you to do it, but I tried to steal it back. It won't let me. Okay, there you go. So what I just did was I integrated a of t, which was, the integral of 2t is going to be 1/2 t squared times 2. So I just got t squared, and the integral of t squared is 1/3 t cubed. So that's the left-hand side. The right-hand side, on the other hand, this is the fundamental theorem of calculus that the integral of a derivative is the original function. So I'm basically going to get v of t minus v of 0, which is that very thing that they gave us. Okay. So now I'm going to evaluate that. I'm going to say t squared I hat plus 1/3 t cubed j hat. And then evaluate at 0 is just minus 0. So I don't have to do anything with that because that's going to give me 0. That's going to give me 0. That's all equal to v of t minus, now I'm going to write that thing, 3 I hat plus 1.00 j hat. So I can say now that v of t is going to be equal to t squared minus 3 I hat. Because pulling that over there, the t squared actually becomes plus 3 on this side, right? Sorry about that. So it's a v t squared plus 3. And then the j, this is going to come over here, and that's going to become a minus. So I'm going to say plus 1/3 t cubed minus 1 period, okay, j hat. Now that is equal to dx of t over dt. And it is a vector. So now we can integrate this just like we did before. So I'm going to integrate t squared plus 3 I hat plus 1/3 t cubed minus 1 j hat. That's all going to be integrated with respect to t. And that's all going to be equal to the integral of dx of t over dt times dt from t equals 0 to sometime later, from t equals 0 to sometime t later. I can integrate this. The integral of t squared would be 1/3 t cubed. So that's going to be 1/3 t cubed. The integral of 3 would be 3t. So that'd be plus 3t. And all that times I hat. And the integral of 1/3 t cubed is going to become 1/12 t to the 4th minus t, because the integral of -1 is just minus t. So this is 1/12, and that's that, and that's j. This is just going to give you x of t minus x of 0, which is what they gave you here. X of 0 is just 1 I hat minus 1 j hat. So I'm going to say minus 1 I hat minus 1 j hat. Now, assuming I didn't make any mistakes, let me see. Oh, one mistake I'm almost certain that I did make is this one right here. This should have had parentheses around it. So the 3 would have been negative, which is that part's correct. But this 1 would have been negative. So this part should have been a plus, which means this should be a plus, which means this should be a plus. Now I have to evaluate this at t equals 0 and at t equals t. Luckily, again, t equals 0 just gives you 0, 0, 0, 0. So that's no big deal. But ultimately, what I'm going to get is x of t, which is this part right here. Okay. This is going to come to this side, and I'm going to get in the I hat component, since this will come to this side, it'll be plus 1. So I get equals 1/3 t that was supposed to be a cubed. I don't know why I wrote a square there. 1/3 t cubed plus 3t plus 1 in the I hat direction. And then plus 1/12 t to the 4th plus t. Now this will become a minus 1 over here, j hat. So now all I got to do is plug in t equal 1 second for all this. So that should be 1/3 plus 3 plus 1, 1/3. So and this one should be 1/12 plus 1 minus 1. So this could be 3 over, this could be 9 over 3 plus 1 over 3 would be 10 over 3. Plus 3 over 3 would be 13 over 3. So I get 13 over 3 I hat. And then this one's going to become just 1/12 j hat. Now that's what it should be, barring any arithmetic errors or whatever. It's not important whether I got the right answer so much, because, you know, I'm just doing this quickly, trying to show you how. The more important thing is this is the process that you got to go through. Does this happen to be one of the answers, by the way? 13/3, which might be called 4 1/3 and 1/12.
Yep, that looks like one of the options.
Okay. So yeah, that's how you do that. And it is a little confusing, but believe it or not, that's one of the few instances where an actual derivation that an instructor does at the beginning of a class comes in super handy, because this is exactly the process I went through to get the x equals 1/2 at squared plus v0t equation.
Yeah, it did not seem like it was that complicated from the numbers they presented. I thought it could just get plugged into one of the standard ones, and I got an answer that was not an option. So
Yep.
thank you for going through that.
No problem. Hopefully that'll help you. I like it. It's a really good problem. Anybody else have any questions? All right, I'm going to call it a day. Once this video finishes recording, and then of course it's got to more or less convert it to an MP4, and then I've got to upload it to my YouTube channel. The video of this should be up after that, and that should be in the next 2 hours, or it might have to wait till tomorrow, just because if it takes too long, I'm not going to wait up for it. So you should have it pretty soon though, okay?
Great, thank you. Have a good night.
Have a good one, everybody. Bye-bye. Nathan and Matthew, y'all didn't have questions, right? Y'all didn't say anything, so I was sort of going to say bye, but I just want to make sure nobody did. Good deal.